Okay, so Flatiron Institute, what is it? It's a new institute that just got recently set up. It's funded 100% by the Simons Foundation. For those who are not Americans, you might not have heard of Simons Foundation, but it's been basically funded 100% by Jim Simons and his family, which was a math professor. For those who've done physics, maybe have heard of Chern-Simons theory, the same Simons. He was a math professor and then math department chair, and then became interested in finance and made a lot of money in hedge fund and decided to donate, I think 98% of his money all into charity before he would, go to better places. And he's decided to fund the Flatiron Institute that was recently set up, and it was, I think, endowment was about over $1 billion. I don't know the exact number, some X number that's very large. And so all of us are basically new scientists hired recently to do fundamental research, and there are 4 different centers. There'll be a 5th. If it hasn't been announced, it will be announced soon. The 4 centers are Center for Computational Astrophysics, which is where I am, Center for Computational Mathematics, which might matter more to the crowd here. Half of it is doing numerical computational methods, and the other one is doing more like machine learning statistics. So recent hires include Stefan Millar and Larisi Condor, though those names you might have heard more. And then we have Computational Biology Center, where we do, a lot of people apply machine learning algorithms or statistical algorithms to methods to actually understand biological systems. And then we have Center for Computational Quantum Systems, which is also sort of similar methods. And then we have a new center called Center for Computational Neuroscience that will set up very soon if it hasn't been announced yet. So we all fairly new. We just recently got ramped up in a Center for Computational Astrophysics, and I'm there working with a bunch of great people. Miles Kramer is a student at Princeton who's also here presenting a poster today. He's right there at the corner. You can wave your hand. He spends a lot of time at CCA, so he can tell you all about Flatiron Institute. We have, I guess, free food every time of the day. So that's the one big draw for the students, especially. Anyway, so my work today, I'm going to be talking about a new approximator, a proximate simulator of the universe using deep learning. The work is obviously not done by me because all the students and postdocs did basically all the work. I'd like to highlight Miles Kramer, who's here at Princeton, and also Peter Bataglia, who's also here working with us on a problem that I'll be describing very briefly. And there's a whole lot of people here, but mostly I would like to stress that a lot of them are students and postdocs who did excellent work. There are a few longtime collaborators of mine in machine learning who are mentioned here: Jeff Schneider from CMU, Marvis Posso from CMU, who's moving to DE Shaw, I hope temporarily, and and also Lawrence Lefasar recently just moved to McGill as a faculty. So less complaining about my talk is my problem. Everything else that's good is done by the students and the postdocs and my collaborators. All right, so the universe as we know it, circa 1900s, you're like, what the heck? People mentioned like 90s and they were like reacting to it, and I said, we'll start with 1900s here. We think 100% of the universe is baryons, and baryons describe everything we know: the protons, the neutrons, electrons, everything you kind of like feel and touch. All these interact not only through gravity, but also electromagnetically, and you have to think about all that modeling if you want to model the baryons. Since I simulate the universe, you have to think about everything. And in the 1970s, we realized that maybe 85% of the matter is dark matter. And for those who don't do pop culture, you might not have heard of this, but actually Avenger had mentioned dark matter very early on, which I will tell you later on if you ask me during dinner, so talk. And we don't know what dark matter really is, but our best guess right now is that they are cold, which means not moving very fast, and they're very massive particles that interact only gravitationally. And the universe as we know it now, which has changed again, and you can see there's a huge chunk that becomes dark energy, which also is mentioned by Avenger. You can now know what I like to watch in my free time. The first scene of Avenger, there's a whole the whole area called Joint Dark Energy Mission that got decimated because I think the Tesseract exploded or something like this, and that's Joint Dark Energy Mission. There's a real mission that got defunded and turned into something else, which I can tell you more, which I'm part of, called WFIRST. And we're trying to understand what dark energy is, and it's for real. It's a $3 billion experiment led by NASA. And We don't know what it is. That's as blank space as we can describe it, which is dark energy. We know so little about it. All I can tell you is that we named it this term to describe our ignorance in the face of the fact that the universe is accelerating its expansion without any really good reasons. It shouldn't be like going further and further apart in the accelerating speed. And if you believe Einstein's correct, then you have to add this negative pressure term called dark energy. Some people will try to say, well, maybe Einstein's not correct and he's wrong, and you can correct Einstein's equation of relativity. So there are two routes that are both equally difficult to do. So that's what we're trying to do. Here is the universe that we actually observe. If you actually dim the light, it actually looks really good. These are the real galaxies you will see from the center if you fly from Earth to the universe. And this has been observed by the Sloan Digital Sky Survey Telescope in New Mexico and Apache Point Observatory. Every single one of these are these galaxies. And these are the data that we want to model and we want to compare against to understand the mysteries of the universe, like dark energy, dark matter. For example, if there's a lot of dark energy, this cosmic web structure, like Halloween's coming up, the spider web structure of the universe, will have more holes. If you have a lot of dark matter, it will be less holes and it'll be like more clumpy. So looking at structures like these of the universe, or the topology of the universe, you will actually have an understanding of these mysterious quantities. So that's what we do. So, yes, please.
How much of the baryons is mass and how much is energy?
I can't hear you.
How much of the baryons is mass and how much is energy?
The baryons are all massive. There are baryons that might not be massive. It's called neutrinos. These are the ghost particles that go through your fingernails. About 1 million of them, well, actually not 1 million of them per second, but a huge number of them going through your fingernails per second. And we've seen this movie. So can we use machine learning to simulate the universe? So that's the title of the talk. And the reason we want to simulate it is so that we can compare the simulation, which is the theory prediction, to the data, which we actually observe with these $3 billion telescopes. So here's a simulation. This simulation costed 30 million CPU hours to run. And you're like, hey, this is very boring when you look at it. But it actually has run with many things at the same time. We have gravity, hydrodynamics. That's the supernova exploding. That's why you have all these shock waves coming out and pushing all these metals around, changing the temperature of the gas, which is what I'm showing right here. And all these filamentary structure are tracking basically the potential. And these are little galaxies blobs, actually. And you can see all these cool things that's happening. But the point is, it's a very complex universe we're trying to simulate. And it costs a lot because you have to do gravity. You have dark matter particles, you have baryons, you have electrons. They all interact with each other, both gravitationally, electromagnetically. And you can also simulate radiative transfer. In this case, they use something called a subgrid models, which is just basically saying we don't understand below the grid, to simulate what is inside, the grid in terms of radiative transfer. All right, enough buzzword, because people are starting to look down at their phones. So what are we going to do first? We're going to do something way simpler. On the left-hand side, it's just a dark matter simulation interacting gravitationally. On the right-hand side is a simulation I just showed you, which has all the electromagnetic stuff going on and hydrodynamics, basically solving all the equations. But you can see and notice, if you squint really hard, the structure of this is following the structure of the left-hand side. Because the dark matter is the backbone of the universe, because so much of it is the matter, and all of it has dark energy. Both of them have dark energy in it. And we're not going to model how supernova explodes, but we'll first solve the gravity problems first. And just Einstein's equations, not so bad this time. So we want to do gravity. We form the backbone of the universe, so we're going to model gravity interactions first with only massive particles interacting gravitationally with dark energy included. So dark matter, dark energy, gravity. That's the three things we're going to deal with for now. What we're going to do on this one is the setup of an experiment. On the left-hand side is the input. It's analytical approximation of nonlinear universe. On the right-hand side is the output. Whoops. The right-hand side is the output, where we actually would simulate and we predict the position and velocities of all the particles evolved under gravity after X number of years. In this case, the age of the universe, 13.6 billion years. And instead of using numerical simulations of, actually in this case, Newton's gravity is perfectly fine because we're not talking about two black holes merging. So we're skipping those situations where black holes are actually getting very close to each other. With smart algorithms to run really fast, we'll use machine learning, in this case deep learning, to learn and interpolate from a large number of pre-run simulations. That's our setup. So right here, on the left-hand side is the inputs. It's just analytical approximation, which is basically what theorists can come up with paper and pencil within like seconds. That's what they can write down. On the right-hand side is the predictions we want, which is the full, it's in 2D slices, but it's actually 3D boxes of all the positions and velocities of all the particles in the box. And the machine learning model that we use is something called the UNet that a lot of people probably find it very vanilla at this point. We did it actually back in when we first tried, and it worked really well, surprisingly well. And we didn't change from it because it worked. This work is published recently in Proceedings National Academy of Sciences for a reason that you'll see soon. I hope that's why they publish it. Then the training set is 8,000 pairs analytical simulation 3D boxes. So analytical is the stuff that we can put down very quickly. The simulations take 1.8 million CPU seconds to generate. So we'll put pairs of them to input to this machine learning model that is just basically a UNet. And we make the predictions. And so punchline plots, what we have going to show you the errors in the displacement field predicted by our model, the benchmark model where everyone uses, and we'll see how they compare. This is the error bar here that actually shows the bluer the better, the redder is best, the worst. Red means, basically a lot of errors, and in this case, it's about 7 megaparsec over h. 1 megaparsec is about 4.5 million light years, for those who want to convert it back to physical distances. Here is the benchmark model, how well it does. This is what cosmologists use when they want to run really fast simulations for the universe. The maximum error there is 7 megaparsec over h. Our model is a lot bluer. Yes?
Can you tell us a little bit about the knowledge? I mean, how many fields are there? Just some idea of what the computation looks like?
Of the generation of the simulations? Yeah, so the simulation are just a bunch of particles, and they're all very massive particles. They interact only gravitationally. We're talking about 100,000 particles interacting with each other in a box.
Okay.
Yeah, it's all 3D. And on the left-hand side is what our displacement field error looks like, and the maximum is about 0.7 megaparsec over h, about 10 times better than the benchmark model that people run right now. And still using, actually. The benchmark model is basically what's being used still right now as currently. And we want to look at it a little bit more statistically, a little bit more mathematically, because we need to convince our colleague that we should do this instead of using our usual benchmark model, which is based on second-order Lagrangian perturbation theory. For those who don't do that, it's just what physicists do and cosmologists do in general to generate large simulations very fast. So we calculated 3 things here. The average power spectrum, oops, I can use this. The average power spectrum of 1,000 simulations. The power spectrum here just basically fast forward, transform the field in 3D and multiply and get the modes. It just means basically if you have a particle here, how likely it is to have another particle over there in excess of the random field. And then the ratio of the true power spectrum, a ratio of the predicted power spectrum to the truth. And here is the error power spectrum. Small scales on this side, large scales on the other side. And here is what we found. So the benchmark model is the blue line. We want to be as close as possible to the green line. So the green is the truth. And you're like, where is the prediction with the machine learning? If you're going to listen at any point, this is a good point to listen. This is the orange line that peeks out tiny bit from under the green line. I keep asking the student to plot better, and she's like, well, there's nothing we can do, because it's basically the same line, except the tiny, tiny bit at the bottom. And if you divide them out, you can see it's slightly better, which means you take the orange line, divide it by the green line, do the same with the blue line, which is the benchmark model. Here's the benchmark. This is where we're doing. And this is the benchmark model currently being used by basically all cosmology experiments. And here's the power spectrum and how much we have improved. The 1,000 simulation were predicted in 30 seconds, and one training simulation took about 1.8 million seconds, which means we're like about 60 million times faster. So we were pretty happy about this. But then we took one step further, and I don't even remember why CEO, the student who was the lead author, decided to do this, but I think she was just going to try and see whether it works. Instead of inputting what the training set has been trained on, the training set would train on one cosmological set of parameters. What it means is that it only knows universe that has 30% dark matter, 65% dark energy, and about 5% baryons. So that's all it knows about. And she decided to put in different cosmological parameters, which means put in 50% dark matter or 10% dark matter, which means the forces are very different. The universe will look drastically different. To give you an example, the position, the density field will look about 80% difference, and the displacement field or the velocity field will look about 30-40% difference for some of these cosmological parameters. So we got really excited to see whether this will even work. So we input this to the same model that has not been retrained, which means it's only seen 30% dark matter universe. It's not seen something else, and see what happens. I was like, well, just try. I mean, there is a model that's already trained. We're not retraining. We did not generate new training sets. Can the learned model extrapolate and predict simulations that do not have the same cosmological parameters? These latent parameters are very, very important. So let's try that. Here is, I think if you're going to see one slide, this slide will be really cool to see, and there's one more slide that's very cool to see later. Check the following, which is the same thing, the power spectrum. Basically, the power is a function of scale. Divide the power spectrum by the truth and the noise power spectrum. The solid line will be the truth of the simulation. The long dashed lines are predictions. The short dashed line is the benchmark, which is second-order Lagrange perturbation theory. And what's surprising to all of us, actually to basically everyone on the project, not just to me, is that the solid line and the long dashed line basically match for all three cases, for all three different latent parameters called how much dark matter there is in the universe. For the 30% is the one we were trained for. For the 10% and 50% were not things that we were trained for at all. So we were very surprised. And the short dashed line is what the benchmark is doing. The same thing you can see is basically all one, all the way to about here for our models, and similar trend in the error power spectrum. So we said, what the heck happened? That's my parental guidance version of what I said when they showed me that plot. And then I said, the model generalized significantly outside the training set, and we did not explicitly use any transfer learning, meta-learning, zero-shot learning, all type of stuff. And maybe there's an overlap of information between these universes, between the 30% dark matter or 10% or 50%. We'll also try 90% dark matter, which is very, very far. And it all worked. So we wonder what happened. Maybe universe is fairly simple, that generalization is possible, or extrapolation by this network is easy. And I don't know why it worked. Can we explain or interpret this generalization, which is what we're trying to talk about a little bit today? So I will stop right here and take some questions. Why not?
Sorry,
it's great.
Before that, when you take these different parameters, things are 30 to 40% different and 80% different.
It depends on, is it 10% dark matter or is it 50% dark matter? But yes.
So when things are mixed, this 10 or 30 or 50, how come it disappears when you look at the power spectrum?
Oh, they're different in the power spectrum. They did not disappear. I mean, when I say 30, 80, that's a log plot. I think that's why I haven't pointed out. Let me show that plot again. The power spectrum is in log scale. So this is density. So the density field between here and here is about, like, if you just plot the differences, it's actually talking about 80% difference as like 30% difference. But it's because it's log plot, so it doesn't look as impressive, but it's in log scale. But that's a great question. I don't know if you guys heard it, but because basically you said there's so much difference, but the power spectrum plot doesn't look so different between the three lines. But I pointed out that it's log scale, so they're quite different. Yes?
I have a question that,
Peter has heard it 3 times. I'm surprised he has questions.
No, like 5 times probably. It's the talk that keeps on giving. Why did you predict displacement and not density if all the stuff you care about is on density?
So we actually tried this density. It didn't work as well. That's the first answer. The second answer in retrospect is that displacement includes information of velocities in addition to the density, because it kind of gives you what happened before and after.
You mean in the supervision of the thing? Because you could even like target both.
We can target both. We haven't tried targeting both.
Density, if that's what you're ultimately going to care
Yeah.
about.
We actually care about both density and velocities ultimately. So displacement was sort of like a good compromise because you get both.
I see.
Yes.
So you run your model once and it predicts how the universe should look stepping forward some, I don't know, a billion years or something?
Yeah, we jumped all the way to basically our analytical model, which is paper and pencil, it is at current time from initial condition of universe, which means jumped 13.6 billion years. We can jump less jumps, which is something that Peter's going to work on with his team, which I'm not working on, directly at least, where do we do like smaller jumps. Right now we just do one big jump, and it's doing really well, so we were kind of shocked by it. And there's a reason why I keep giving this talk, because I haven't solved it, and I'm going to show you why. So we tried to interrogate the learn model. I'm not going to talk about all three things I mentioned here, which is basically simple analytical cases that are not in the training set explicitly, and see how these cases agree with us, with what we actually understand. Try to locate invariances in the system and locating where the information is coming from, what the model has learned. So we try that. These next three plots are the most complex plots in this talk. I would debate it very strongly whether I should show it, given it's after lunch, but I'll try. This is when you have two modes. So all the training set has particles, like 100,000 particles interacting with each other. But what we here showing is a two plane wave coming in and interacting with each other. Two plane waves this way. And they're of the same amplitude, but coming in different directions. And see how they interact with each other. So what we're showing here is the Fourier amplitude or curl free of displacement field. But don't even worry about what that really means as a function of scale. What it's trying to show you is that when we have these two plane waves interact, you know physically what those results are to first order. The zeroth order is that two plane waves come in, two plane waves come out. That's the first point, which is the first point, which everything agrees. Deep learning, simulation, the theory, the initial plane waves, basically you expect is more or less there. Then you have the next part, which is two plane waves come in, they interact with each other. And that interaction term is as far as the Lagrangian theory for like classical mechanics can predict. And we agree with it from the deep learning side, which is interesting for physicists because we never taught it Lagrangian mechanics. I mean, I did not, because I barely understand Lagrangian mechanics myself. It's a long time since I've taught Lagrangian mechanics. And then the next question is, what else is there, right? Because the next step beyond this scale, which is beyond this k scale here, we don't know in Lagrangian theory. And we can only do it from simulations. We can show you what the simulations predict. We can show you what deep learning predicts. But we do not have a theory for it. So if we learn anything for the next set of scales, we can actually feed it back to classical mechanics, or when I say classical, Lagrangian mechanics. And here's what we saw. Here's the simulation predictions, which is when you just ran two plane waves together. The green dot is what the deep learning is showing us. But notice that there's a lot of possible noise here because the simulations are not perfect. While the simulation here that we ran is much simpler simulation because it's literally two plane waves interacting with each other. This green dot is what machine learning has, well, what the unit has learned after it observes 8,000 simulations pairs. So they're coming from very different angles. It's like you've seen 8,000 universes versus I just ran a simulation of two plane waves interacting. And they're coming up about similar scale. So this must be a bunch of noise, but we don't know what they are. And we're trying to figure out if we can tease out some information about the scale of amplitude. Even amplitude there is unknown to physicists. And classical mechanics has been around for a long time. So if we can come up with something new, even for classical mechanics, it's pretty cool. That's like telling you found a new term for Newtonian mechanics. So this is what we're trying to do. Maybe with machine learning, but maybe not, because there's a lot of noise, and we have to figure out how to remove the noise at the same time. All right, those are the difficult plots. It's passed. Now it's a little less difficult. We try to test whether the machine learning unit has learned invariances, any invariances. So we input plane waves in 3 different directions, feed it into the unit again. That was not ever retrained, it was only trained once. And we found that they all predicted the same power, which at some level is telling you that the rotational invariance is learned automatically by the model, which is also surprising. Anyway, here are the few things that I would like to mini conclude right now, because there's a lot of stuff that we could try, is that first of all, it seems like the model is able to generalize outside the training set. We now have cosmological simulations of particles interacting gravitationally that run 30 million times faster than usual, and for a variety of latent parameters. And the model has learned rotational symmetry, and it agrees with Lagrangian perturbation theory very well. And it's telling us something more, which we don't understand. What should we do next? And here's what we have. Originally, we have analytical approximation to full MOS simulations, 1.8 million CPU seconds. Now it's 0.03 CPU seconds, and it generalizes outside the training set. All right, I'll pause right here. Yes?
You say rotational symmetry, but really what it showed is that x, y, and z are the same. But if you go...
We haven't rotated further, but we should try. This is a great.
I would guess it's not. CNN is there now.
We can try. I don't know, actually. It's a really good point. Like maybe CNN because it's doing convolution in just these ways.
Yeah.
So we should check the SO3 group, basically. Yeah. Any other questions? I'm happy to take questions along the way. Yes?
Is your input 3 layers? Like are you separating the baryonic matter and the dark matter and dark energy into different inputs, or?
No, they're all in just one box. So they're just all the particles in one box. They're not separated. So, but for the simulations we just showed you earlier, it is only dark matter with dark energy involved, but there's no baryons yet. But the next part of the talk, which I promise we'll talk about something more than what Peter has heard 5 times. You actually heard this one time at least. And then we have dark matter, we have dark energy, and we can simulate the baryons. It describes everything we know, right? So we have the baryons that we have to model. As I just said earlier, we have the dark matter, we have gravity, we have dark energy, but we don't have baryons in previous simulations. And so what do we do here? So what we did just now is to make the left-hand side simulations run really, really fast, like 30 million times faster. And the right-hand side, as I mentioned early on, takes 30 million CPU hours to run. This one takes 1.8 million CPU seconds, which is quite different. This is hydrodynamics, which means and gravity, so which means solving all the equations for the physicists in the crowd. If you don't care, it's just a really hard simulation to run. There are about 3 of them in the world. So, yes?
Sorry, I had a question on the previous slide. So I was too slow to
don't worry, I'm
question while you're still on it. My question was, you showed that this had good extrapolatory behavior in terms of the ratio of dark matter to baryons.
Well, dark matter to the total content of the universe.
Okay, dark matter.
Some ratios.
But to what extent were you actually extrapolating in the input features that the neural network was using? Because I could imagine that if they sort of are all still in the same density range, then that's
the plot that I removed, but I didn't show you guys. But I mentioned it by orally. Is that the density of the particles? They were about 20% to 80% different when you go to these 2 parameters. So from dark matter equals to 30% to 10% or 50%, the field has changed in the density field by about 80% or 30%.
In terms of the total range that's covered?
Yes, exactly. And in terms of the velocities, there's a different range that I can describe.
Oh, interesting.
Yeah. So it's not a small extrapolation. Yeah. Any other question about the previous part? Yes, Cecilia.
Something about the network, because I'm not familiar with your net.
There's something about the neural
Can you
net.
say something about the network?
Oh, yes. I've totally skipped this part partially because I thought the crowd has so much expertise in it, but I should really talk about it. It is a very simple unit. It has, they say this is where the input is, the output is the same size. They are 3D boxes on both sides. The left-hand side is actually a 3D box of displacement. And and the right-hand side is 3D boxes displacement, and then you basically have multiple convolution layer, and you go down to the bottom, you go back up again. There's a bunch of concatenation in between, so that you actually take information at the output from the input too. And later on, we'll show using similar networks, so it's good that you asked me right now. Yes?
A simple question. You train the network to predict after a fixed number of time steps? So the network takes a current state of the universe and predicts the states at some later. So it's a fixed time step?
So this is a great question. So what we did is that from the initial condition of universe, which is time 0, to current day, we took this big step, and the input is already what theorists can write down paper and pencil. That's why I say analytical approximation of current time universe. That's our input. And then we bring it to what you need to do what you will see if you run the n-body simulations, the gravity simulation over 13.6 billion years from the beginning of universe. So does that make better sense? Okay, cool. But great questions. That means I'm waking people up too, hopefully. All right. I'll move back down to the pretty simulations. I always try to put movies towards the end of the talk because everyone falls asleep anyway. I do that too. Dark matter simulations, we got that. Hydro simulations, which is way harder. We're hopefully trying to do it. So that's what we did, which is what we hopefully will do even better. On the left-hand side is the gravity simulations. We want to take the gravity simulations and map it to the hydrodynamic simulations, but they have the same initial conditions. On the left-hand side is dark matter distribution, and you can see that it's way denser than the right-hand side, which is the galaxy distribution. If you project it in 2D and just take a slice out, it's super sparse. And you're going from gravity only plus dark matter and dark energy, these basically unknown stuff, to gravity plus hydrodynamics plus dark matter, dark energy, and baryons. This is recently accepted by the NERPS workshop that Kyle and I are also co-organizing. So how do you do from dark matter to galaxies? Left-hand side is all dark matter input. We want to have the output, which is the target here, is super sparse, from dark matter distributions to those bright, bright galaxies. It was surprisingly hard when we first tried it, and because I think there's such a sparsity problem. There's just not many galaxies on the right-hand side that you're trying to predict, and there's lots of dark matter particles on the left-hand side. So we had to create a two-phase model structure where the first phase is an inception net. We tried a bunch of different ones, but the first phase, in the end, we decided to use inception net, which basically say whether there is a galaxy or not in a pixel, which is verifying pixel. The second phase is a modified unit architecture that regresses and say for the pixel that will have a galaxy, how many are there? So that's the unit architecture that we modify slightly by removing concatenation on the top. And it was surprising when you sort of play around with them, you realize if you remove some concatenation layer versus not the other ones, you are drawing in information at different scales. It's just fun for physicists to play with. And here's what we got. Input, target, and prediction. And you can see, visually it looks pretty good, but given that resolution you're seeing from the back, you probably can't trust me. So we did something more analytical and more quantitative. Again, the power spectrum, sorry, this is what cosmologists do all the time. The power spectrum of the predicted simulations and the ratio to the true power spectrum. The whole process of training plus prediction takes 3 hours. One training simulation takes 30 million CPU hours to run. We have about 3 of them in the world. So let's try to make them faster. We actually end up doing really, really well. So orange is the benchmark model, which one of the postdocs on the paper actually creates. And he completely transformed into machine learning convert right now because of what happened. That's his model, which is the state-of-the-art model, by the way. And the green line is the truth, and the blue line is our method. It's not perfect, but it's way better than the benchmark model. And again, this is log scale as a function of scale, log scale on the y-axis. And you can see that actually the orange doesn't perform badly in the large scales, which is what cosmology has been doing for a long time because we cannot model anything beyond this scale. So anything beyond here, we always smooth them out this nice pretty picture of what I just showed you of the universe, we smooth everything out below 30 megaparsec, which is about 100 million light years. We smooth everything below it because we can't model them. So that's why, because the orange line is not modeling well the truth, because we know they were different, and we smooth everything below 100 million light years usually. And now I think we can just smooth it down to, 10 million light years or so, which is a significant step forward. And again, here is the benchmark model. Here's how we're doing. And that's one, which is the perfect.
Can I ask a question?
Yes.
So you said there are only 3 simulations available. So you train
We only train on one.
only with one.
That's also the beauty of it. It's only took one. Well, one really expensive, complex simulations. I mean, the people who create them are like, there's a team of 20 people just to make that simulation work. And then there's another team of 20 people just to make sure it runs on some cluster. And they need like supercomputing time to just even run it. I mean, we don't have Google time. Hint, hint, to anyone who has Google access. What's next after predicting all the galaxies, right? So we want to predict the gas. And you're like, why the gas? Because we observe the emission from hydrogen in many, many telescopes and many observations. Here is one of them. This is in the Atacama Desert. It's called the Hera telescope. It has many, many radio dishes, and it observes the emission in radio from the hydrogen. And there are many of them. And so what we did is that we did something similar as before, but this time we modeled the gas. Our results modeling the gas in hydrodynamic simulations are accurate across 9 orders of magnitude. The simulation generation with the physics takes about 100 million CPU hours because we use all 3 of them. And the predictions took 2 seconds. And you can tell me which one took 100 million CPU hours, which one took 2 seconds. This visual test is impossible to win, of course, but I will show you why our results, I will show you a plot that hopefully convinces you that our result agrees across 9 orders of magnitude. From extremely high density region, which is like where all the stuff is, and when there's like nothing. Yes, Peter?
These are all displacement fields again?
These are not displacement, these are actually hydrogen density field.
Oh.
So no displacement involved this time. This is a scaled effective mass of hydrogen on the x-axis. And the target is the blue line. And the benchmark, which is what our postdoc sort of bet his faculty application on, is the benchmark, the black line. And he's working with us and realized that we can do this prediction, which is the red line, very, very quickly within hours, basically. And it's agreeing way better. And the error bar is actually accurate error bar, just given the size of the volume that we actually use in the training set and the test sets. This is,
Can you say it again? Where do the errors come from?
It's just the fact that we have limited volume of the universe that we have for training sets and test sets.
Excuse me?
Yes?
Error bars, on the left is pretty off, no?
Yeah. So there is, you mean the error bar on the left? You mean these guys?
Yeah.
I think it's
from the prediction, the error bars.
Mm-hmm.
What exactly are they indicating?
I think the error bars here, we're just calculating how many, so basically for each bin, there is how many cubes of overdensity of that density. So this is sort of like a dense hydrogen density. So it depends how many are there in each bin, so you have a different error bar.
How can it be negative?
Oh, the error is not negative, it's just the size.
The effective, how can the effective mass be negative?
Oh, it is a scaled one. They scale to a different constant. So this just to show the plot a bit better. And so this is what we've done so far, and we're getting close to the end of the talk. We have analytical approximation of the universe with gravity only, which is basically paper and pencil. Usually it takes about 1.8 million CPU hours to generate the full n-body simulations. And it takes about 100 million CPU hours, depending on the volume the universe want to cover, to generate the galaxies or the gas. And what we did is that we turned them into 0.03 seconds. That extrapolates well, at least in the parameters we looked at. We looked at 2 of them, which is one of them is called the dark matter density parameters, how much dark matter there is in the universe. The other one is called AS, which I'll describe later if people are interested. and then 1 second to this and 2 seconds to that for the galaxies and the gas distributions. So now we can simulate the universe with deep learning, to first order at least. Can we use deep learning to learn about the forces in the universe given out data? So I'll usually advertise a poster by Miles and talk by Peter Vitaglia about this. And I thought this is a really boring plot because nobody's going to read it. So I decided to use Miles' tweet about the paper, which is like recently accepted for oral presentation in NERP's ML for Physics workshop. See you in Vancouver very soon. And he can explain to you with his poster about how we can actually do this properly to extract physics from trained graph network and improve the zero-shot generalization. And I'll conclude here. If deep learning can indeed approximate simulations and extrapolate outside the training set parameters, it would dramatically expand the boundary of what scientists can do these days and possibly other areas, because this idea of comparing simulations and data is basically overwhelmingly everywhere. Extrapolation and generalization outside training sets is not guaranteed. We don't know why it happens in our case and whether we can make this generalization transfer more robust. Can we design architecture that allows this generalization happens more often at least? Learning natural laws within the data set itself can be further improved by imposing physical priors even on the model itself. So see poster by Miles and talks by Peter. There are possibly more deep learning can do in terms of picking what simulations are most interesting to run or what observations are most useful to make, maybe something with reinforcement learning, which I didn't talk about. There's immense hype and possible immense potential in the crosstalk between machine learning and sciences. So you should come to the NERPS workshop that Kyle and I are also organizing. All right, thank you guys.